Hi everyone, I hope you are fine and welcome to the second lecture about the carboxylic acid and their derivatives. And our subject today is about the nucleophilic acyl substitution. The carboxylic acid are compounds that contain an acyl group bonded to an electronegative atoms, as well as carboxylic acid derivatives that can be prepared from them is acid chloride, anhydride, ester, and amide. Now, firstly, I want to understand what meaning nucleophilic acyl substitution. And look here, he said the carboxylic acid are compounds that contain an acyl group. What meaning acyl group here? Bonded to an electronegative atom. Acyl group meaning you have R alkyl or allyl compound, single bond carbonyl group, carbon double bond oxygen. This part is the acyl group bonded to an electronegativity atom. Here, if you replace this Z with OH, it will be carboxylic acid. And you know the carboxylic acid group is R single bond carbonyl and then OH. Then is acyl group bonded to the high electronegative atom. And then he said, as well as carboxylic acid derivatives that can be prepared from them, acid chloride, anhydride, ester, and amide. He said carboxylic acid derivative. Okay, مشتقات الحوامض الكربوكسيلية. Then, if you replaced this OH with chlor, it will be acid chloride. Acid chloride. And if you replace the Z group with oxygen, carbonyl R group like this, oxygen, carbonyl R group, it will be anhydride. And the acid chloride and anhydride are the carboxylic acid derivatives. And if you replace the Z group with OR, it will be ester compound. And if you replace the Z group with NR2, of course the R here, maybe it will be hydrogen or alkyl. It will be amide. That meaning we have amide, ester, and anhydride, acid chloride. All of them is carboxylic acid derivatives. Again, our subject is nucleophilic acyl substitution. That meaning we have here acyl group and nucleophilic acyl substitution. And you have nucleophile, and we want to replace this nucleophile with Z group. That meaning nucleophile acyl substitution. Okay, that meaning we have a new nucleophile, it will be substituted on the acyl group and remove the Z group. Then anhydrides contain two carbonyl groups joined by single oxygen atom. Look, here we have two carbonyl groups joined by single oxygen atom. And we have two types of the anhydride. We have symmetrical anhydride, that meaning this group here, it will be exactly like this group in the other side. It will be symmetrical, that meaning this side will be equal to this side if you make this molecule two parts. Okay, that meaning that both of them, it will be identical alkyl group bonded to the carbonyl carbon. And we have mixed or unsymmetrical anhydride like this molecules. This the alkyl group, it will be not identical, it will be different. Look, we have here methyl and we have here methyl, and also we have the last type is the cyclic anhydride. Look, here we have cycle, and the ring of cycle contain from the carbon, oxygen, carbon. It will be cyclic anhydride. And then we have amides, and as I explained for you, the amides is the acyl group bonded to the an nitrogen atom, and this nitrogen atom may be substituted to hydrogen, or one hydrogen and alkyl group, or two alkyl group. And for this reason, the amides classified to the three types, dependent on the number of carbon atoms bonded directly to the nitrogen atom. And here we have just one carbon bonded to the nitrogen, it will be primary amide. And here we have this carbon and this carbon bonded to the nitrogen, it will be secondary amide. And here we have one carbon, 1, 2, 3 carbon atoms. For this reason, it will be tertiary amides. And also the amide and the ester can be found in cyclic compound. And for the ester cyclic compound, it will be called lactones, and for the cycloamide, it will be called lactams. And the ring size of the heterocyclic is indicated by the Greek letter. An amide in 4-member rings is called beta lactams. Beta lactams. Why beta lactams? Because the beta carbon here, we have the carbonyl group, and we have the alpha carbon is the first carbon atom bonded directly to the carbonyl, yes? And the second carbon, it will be beta, and the other it will be gamma. And look to the beta carbon is bonded directly to the heteroatom. For this reason, it will be called beta lactam. Look to here, we have alpha, beta, gamma. Here, this cycle, 5-member ring, it will be called gamma lactam. And the same thing for the esters. We have alpha, beta, gamma, and we have alpha, beta, gamma, and theta lactones, gamma lactones. That meaning the alpha, beta, gamma here is used to indicate for the size of the ring. All of these compounds, I mean here all the carboxylic acid derivatives, contain an acyl group bonded to the an electronegative atom Z that can serve as leaving group. As a result, these compounds undergo nucleophilic acyl substitution. And if you remember the aldehyde and ketone, we said aldehyde and ketone don't undergo nucleophilic substitution because they have no leaving group on the carbonyl carbon. Okay, what meaning this? Okay, this the acyl group. If I said we have hydrogen here, it will be aldehyde, yes? And if I say to you the hydrogen is good leaving group or not, of course your answer will be not. Why? Because hydrogen minus is very strong base and not stable. And if I say to you this the hydrogen is R group, now it will be ketone, and this alkyl group, it will be good leaving group or no, like it will be R minus, that meaning carbon minus, and the carbon minus is stable or no, not stable, because R minus is a strong base. And for this reason, aldehyde and ketone cannot be undergo nucleophilic acyl substitution. Then, if we have here halogen, like chlor, then the halogen is good leaving group or no? Of course, the halogen is good leaving group or good leaving group, because the halogen minus with negative charge, it will be stable because the high electronegativity for the hydrogen, for the halogen, atoms. For this reason, it will be good leaving group. The same thing for the nitrogen, for the amide, the same thing for the ester compound. All this are good leaving group. The same thing for the anhydride compounds, because we have like this anhydride. All of this group are good leaving groups. For this reason, the carboxylic acid derivative can be undergo to the nucleophilic substitution. And he said here, because carboxylic acid derivative all contain an atom Z with non-bond electron pair, their resonance structure can be drawn for the RCOZ like this. This unshape of electron, if you open the pi bond to the oxygen atom, we will have positive charge, and the unshape of electron it will be making new pi bond, and the positive charge it will be converted to the Z atom. For this reason, it will be stable. Why? Because the resonance structure. And if you compare the carboxylic acid derivative with the aldehyde and ketone, it will be for the acid carboxylic derivative, there's a 3 resonance structure. But for the aldehyde and ketone, there is just 2 resonance structure. Again, for the carboxylic acid derivative, look, we have a 3 resonance structure, 1, 2, 3. But for aldehyde and ketone, there is just 2 resonance structure, and there is no unshape of electron on the hydrogen or the alkyl group. Then for aldehyde and ketone, if I open this pi bond to the oxygen, it will be negative charge here, and we have positive charge, and there is no additional resonance structure. There is no unshape of electron here on the hydrogen or on the alkyl group to give you another resonance structure. For this reason, the carboxylic acid derivative are more stable than aldehyde or ketones. Now you know why the carboxylic acid derivatives are more stable than aldehyde and ketone, and you know the answer. Now, if I say to you, anyone is more stable than the others for the carboxylic acid derivative, the acidic chloride or the anhydride, or the carboxylic acid esters, or the amide. Here you have to think about anyone is easy to enter to the resonance structure or to give the 3 resonance structure. Now look to here, the more basic Z, we talk about the chlor or the oxygen or the nitrogen, Z, the leaving group, the more it donate is electron pair, and the more resonance structure 3 contribute to the hybrid. Again, the more basic Z is, the more is donate it is electron pair, and more resonance structure 3 contribute to the hybrid. What he mean here? He mean you have this, the 3 resonance structure, this 1, 2, 3. Okay. Now, anyone, this is the Z group. Any Z group is easy to donate the unshape of electron. That meaning is easy to give you the 3 resonance structure with the hybrid structure. For this reason, if you replace the Z with the halogen, the chlor, it will be not easy to give the unshape of electron, because the halogen is high electronegativity atom. But if you put, or if you replace the halogen with the nitrogen is less electronegativity atom than the halogen, and the nitrogen in this case it will be easy to give you the unshape of electron to give you the 3 resonance structure with the hybrid structure. And to determine the relative basicity of the leaving group Z, we compare the pKa value of the conjugated acid as it given in table this below, and the following order of the basicity. It will be like this. It will be for the amide, it will be increase the basicity, and this it will be high basic, and this it will be low basic. Why? Or this it will be strong base than this. This it will be weak base, and this it will be strong base. Why? Because the halogen is high electronegative atom, and it is not easy to give you the shape of electron. And here we have a resonance structure, and the negative charge is not delocalized, is not localized on the oxygen atom. It will be delocalized during resonance structure. And here we have the hydroxyl group, and we have the OR group minus O alkyl group for the ester carboxylic acid, and they will be similar if you compare the basicity between of them, but this is slightly less basic than this, because here we have the alkyl group, and you know the alkyl group is donating group, make this negative charge here high density, and it will be easiest to give the shape of electron than the hydroxyl group. For this reason they put the hydroxyl and then the ester group. And finally we have the negative charge on the nitrogen, and if you compare the electronegativity for the nitrogen atom with the oxygen or the halogen, of course the nitrogen is low electronegativity atom, and for this reason it will be strong base, give the unshape of pair of electrons. And here in this table also increase the basicity from the up to the down, and if you compare to the conjugated acid, you know the HCl is the strong acid than the alcohol, for example, and the pKa value for the HCl, it will be -7 if you compare the pKa, and very low with the alcohol and the amine compounds. Because the basicity of the Z atom determine the relative stability of the carboxylic acid derivative, the following order of stability result. For this reason, the amide it will be high stable, and the chlor it will be low stable. Why? Again, dependent on the basicity of the Z atom here, the Z atom here, Z atom, dependent on the basicity of the Z atom, and anyone it will be enter or give you the 3 resonance structure more than the others. Thus, an acidic chloride is the last stable carboxylic acid derivative, because the halogen minus or the chlor minus is the weakest base, and amide is the most stable carboxylic acid derivative, because the minus nitrogen is the strong base. And finally, as the basicity of the Z increase, the stability of the carboxylic acid derivative increase because of the added resonance structure stabilization. Any resonance stabilization? This, the 3-1. This 1, 2, 3. This the 3 resonance structure for the stabilization. Now, naming an acidic chloride. Acidic chloride are named by naming of the acyl group and adding the word chloride. And there is 2 different methods to give the name for the acidic chloride. It's dependent of your compound is acyclic or cyclic compound. For acyclic acidic chloride, change the suffix IC acid of the parent carboxylic acid to the suffix UL chloride. Look to here. If you replace the chlor here with the OH group, it will be acetic acid. Yes, acetic acid. Now change the IC acid to the UL chloride. It will be acetyl chloride. Acetyl chloride. And the second method, when the carbonyl chloro group is bonded to the ring, change the suffix carboxylic acid to carbonyl chloride. Now, look, if you have here OH group, not halogen, it will be what? It will be cyclohexane carboxylic acid. Now, change the carboxylic acid to the carbonyl chloride. It will be cyclohexane carbonyl chloride. Cyclohexane carbonyl chloride. And look to this compound. Is a cyclic compound. There is no cycle here. Acyclic. And if you have here OH, it will be what? 2-methyl butanoic acid. Now change the IC acid to the YL chloride. It will be 2-methyl butanyl chloride. 2-methyl butanyl chloride. Naming of anhydride. Symmetrical anhydride are named by changing the acid ending of the parent carboxylic acid to the word of anhydride. Look, this part is derived from the acetic acid, and this is the same for this part. For this it will be acetic, not acid, acetic anhydride. And for the mixed anhydride or the unsymmetrical anhydride, which are derived from the two different carboxylic acid, are named by the alphabetizing the name of both acid and replacing the word acid by the anhydride. Look, this part is derived from the acetic acid, and this part is derived from the benzoic acid. For this reason, it will be acetic benzoic anhydride. Acetic benzoic, A and then B, alphabetically, okay? Acetic benzoic anhydride, not benzoic acetic anhydride. In this case, you know the name for the anhydride is not symmetrical structure. Naming an ester. An ester has two parts to its structure, each of which must be named. An acyl group, this RCO, and the alkyl group, whereas the alkyl group is directly bonded to the oxygen atom. Both of the parts must be named. And it is very clear from the name in the AOPAC system. At the end we have ATE as a suffix. ATE. If you see the ATE, that meaning this compound is ester compound. For example, give the name for this compound. We have here acyclic ester, and we have here ester structure but with cycle, is ester with cyclic alkyl group. In this case, I will give you just a note to give the name for the any ester compound. Firstly, you have to name this alkyl group directly bonded to the oxygen, and then this in number 1, and then you have to name this the alkyl group bonded to the carbonyl. Step number 1, name the R group bonded to the oxygen atom as alkyl group. Okay, look, this is methane, ethane, 2 carbon. It will be ethyl group, this ethyl group. Okay, and this is tertiary butyl group, tertiary butyl, ethane, propane, butane, 4 carbon atom. It will be tertiary butyl group. Second step, name the acyl group by changing the IC acid end of the parent carboxylic acid to the suffix -ate. ATE. Now, to name the acyl group, it will be second part of the name. For this reason, look to this. This part is derived from the acetic acid. Acetic acid. It will be acetic acid. It will be acetate. Change the IC acid to the ATE. Acetic acid will be acetate. Ethyl acetate. Ethyl acetate. And this part is derived from the cyclohexane carboxylic acid. It will be converted to the IC acid to the 8 cyclohexane carboxylate, and the name it will be tertiary butyl cyclohexane carboxylate. Naming of amide. As we know, there is three types of amide. There is primary and amide, secondary and tertiary. For primary amide, there is no problem, just replacing all the ending for the carboxylic acid, IC acid, OIC acid, or oleic acid to the amide. This acetic acid, it will be acetamide. Benzoic acid, it will be benzamide. And this 2-methylcyclopentane carboxylic acid, it will be 2-methylcyclopentane carboxamide. Okay, that meaning change all the suffix related to the carboxylic acid to the amide. And if you see the amide at the end of the name of the compound, that meaning is amide compound, of course. But for the secondary or tertiary amide, there is two parts in the for the name of the compounds. The first part to give the name for the R group or the alkyl group that bonded to the carbonyl, and the second part is related with the R group is substituted on the nitrogen compound. For example, this it will be a secondary or tertiary amide depending on the alkyl group. This R group is the hydrogen or the alkyl group. To give the name for this structure, number one, you have to give the name for this alkyl group that are bonded to the nitrogen atom. This it will be number one. Okay, number one, the first part of the name. And secondly, you have to give the name for this alkyl group. This it will be number two. This is a special case for the secondary or tertiary amide. For more understanding, I will explain for you how to give the name for these two amide structures. Name the alkyl group or groups bonded to the nitrogen atom of the amide. Use the prefix N like this, N italic and hyphen preceding the name of each alkyl group. To the names of the alkyl groups form the first part of each amide name. That meaning the name of the alkyl group it will be right, or it will be the first part of the amide name. For the tertiary amide, we have some problem here for the tertiary amide. If you have this tertiary, if the alkyl group are identical, the same alkyl group, we will use di. But if the alkyl group here are not identical, we will use N italic hyphen for each of one, and we will writing as alphabetically. Okay. For tertiary amide, use the prefix di if the two alkyl group on the nitrogen are the same, identical, same. If the two alkyl group are different, not identical, we have to alphabetically the parts name, and we put N hyphen for each one. Look to this here, N carbonyl, this compound, this group, it will be ethyl, and we will put N, it will be N-ethyl, that meaning this ethyl is substitute where? Is substitute on the nitrogen, and that meaning the ethyl on the nitrogen. Okay, and we have here two methyl group, it will be NN dimethyl, that meaning on the nitrogen twice we have dimethyl. And finally we have to name the acyl group with the suffix amide. Change the IC acid or the oic acid of the parent carboxylic acid to the suffix amide. Put the two parts of the name together. It will be together. That meaning N, look, N-ethyl, N, we have on the nitrogen ethyl, formamide. This formic acid, it will be formamide, or formamide. Okay, formamide. That means N-ethyl formamide. This change the benzoic acid to the benzamide. This is the benzoic acid. It will be benzamide. And what we have here, we have methyl group. NN dimethyl benzamide. NN dimethyl benzamide. Now look to these two examples. Okay, now this we have meth prop bute pentan hexane. We have hexane 7 carbon atoms, and if this chloride is derived from the hexanoic acid, if you put here OH, it will be hexanoic acid. Now change the IC acid to the UL chloride, it will be hexanoyl chloride. Okay, now what we have here as a substituent, we have on the carbon number 2, not this 1 2, on the 2 and 3 4, on the 4 we have dimethyl hexanoyl chloride. Now the second example is ester compound. Look, here we have 1 2 3 4 5 pent. It will be pentanoic acid, if we, because it's derived from the carboxylic acid. Now change the IC acid to the ATE, it will be pentanoate. Okay, pentanoate. And now we have to name the alkyl group bonded to the oxygen atom. This alkyl group is isopropyl group. For this it will be isopropyl, and we have substituent here on the carbon number 2, don't forget that, it will be isopropyl 2-methyl pentanoate. Isopropyl 2-methyl pentanoate. Look to the ATE, it will be ester. And here we have many examples. Like this is acetic chloride. It will be 5-methyl heptanoyl chloride. We have 5 here, methyl heptanoyl chloride. And here we have amide, and this amide is tertiary amide. We have methyl here, and we have isobutyl here. It will be N-isobutyl N-methyl butanamide. And here we have ester compound, it will be ATE, asterate, propanoate. Isopropyl, we have this isopropyl and propanoate, 1 2 3 carbon propan. It is from the derived from the propanoic acid. It will be isopropyl propanoate. And we have also here ester compound, also secondary butyl. This is the secondary butyl 2-methyl hexanoate, and we have here anhydride, unsymmetrical anhydride. For this reason, this is derived from the acetic acid, and this part come from the formic acid. It will be acetic formic anhydride. And also here we have amide, secondary amide. We have on the nitrogen we have ethyl, N-ethyl, that meaning on the nitrogen we have ethyl hexanoic acid, not hexanoic acid, amide. It will be hexanamide, is derived from the hexanoic acid. And here you have to try to resolve this problems as homework for you. Physical properties for the carboxylic acid derivative. You know carboxylic acid derivative has the carbonyl group, and the carbonyl group is polar group. For this reason, it will be give you dipole-dipole interaction. And for the amide compound, primary amide has ability to make hydrogen bond with the carbonyl group for the another molecule, like this hydrogen bond between the hydrogen and the nitrogen for the first molecules with the oxygen of the carbonyl for the second molecules. For this reason, they have ability to make the hydrogen bond, and this give the amide compound high boiling and melting point if you compare the secondary primary amide with the tertiary amide. And you have here a question: explain why the boiling point of this amide is the primary. Look, 221 is significantly higher than the boiling point of this structure, even though the later compound have higher molecular weight and more surface area. Why this compound has a high boiling or melting point than this? Your answer must be explain the ability to make the hydrogen bond for this compound, and this amide there is no hydrogen bond between the molecules. And also, if you compare the amide with the other carboxylic acid derivative with similar molecular weight, look, for the amide we have higher boiling or melting point if you compare with the other compound, because the ability to make the hydrogen bond. And then the carboxylic acid derivative are soluble in organic solvent. Most carboxylic acid derivative having equal or less than 5 carbon are water soluble, because they can hydrogen bond with the H2O. The water molecule can make hydrogen bond with the carbonyl group. And more than 5 carbon are water insoluble, because the nonpolar increasing the nonpolar of the alkali group. And you know the nonpolar compound can be not soluble in the are not soluble in the H2O solvent as a solvent, dependent on the polarity of the alkali group. And I will stop here introduction of the nucleophilic acid substitution. Please study this lecture, and if you have any question, please join our meeting at Tuesday at 11 a.m. and see you. Bye bye.